Okay, we are ready for 4.3, differentiating the natural logarithm. So the derivative of the natural log of x is just 1 over x, 1 over its argument. But remember, you can take the natural log of another function. So we may need to use the chain rule, sometimes the product rule. So you just have to determine where is that natural log and how is it being used. So let's do some examples. So in example A, we're taking the derivative of 3x to the 5th times the natural log of x. So again, we have a product here. And just as a reminder, if we have two pieces being multiplied and we want to take the derivative, like a function times a function, then we take the derivative of the first function times the second function as it is, plus the first function as it is times the derivative of the second function. So in this case, we'll consider the 3x plus 5 to be f and the natural log of x to be g. So let's take the derivative of the first part. That would be 15x to the 4th times the natural log of x. Notice we're keeping the second part as itself. Then we keep the first part as itself, so plus 3x to the 5th times the derivative of the natural log of x. Now we have to clean it up. We get 15x to the 4th natural log of x plus, and in that second part, 2 of the x's there will reduce, so we get 3x to the 4th. As far as I'm concerned, you are done. So again, this is the first derivative for both of these. If you want to factor out a 3x to the 4th, you can, but you don't have to. Now we want to take the derivative of the natural log of the argument 3x squared plus 2. This is a function within a function. So remember the chain rule. We take the derivative of the outside function. So since the outside function is a natural log, we will take 1 over 3x squared plus 2 as it is. But then we have to multiply it by the derivative of the inside function. And in this case, 3x squared, that derivative would be 6x to the first. And the derivative of 2 is 0, so he doesn't show up. So we can clean this up. We can get 6x over 3x squared plus 2. Be careful, go back to your algebra. We cannot reduce the x's or the 3 and the 6 or even the 2 and the 6 here because of that plus sign. You can only reduce factors, things that are being multiplied or divided, not things that are being added. So let's take a look at C. Now before I would take the derivative of this, I would rewrite that argument as 4x cubed plus 1 to the 1/2. You can leave it as to the 1/2 here, or you can put the 1/2 in the front. That might make life a little bit easier for you when you're taking the derivative. Remember, that's a property of natural log. And so when we take the derivative there, we can take the derivative of the outside function. So that 1/2 is part of that outside function times 1 over the 4x cubed plus 1. But that inside function, we have to use the chain rule, multiply by that derivative. So the derivative of 4x cubed would be 12x squared. And the derivative of that 1 is 0. So now we clean it up. But notice, I did not write y prime until I actually started doing the derivative. These two here, from here to here, I'm just rewriting the square root as to a power to 1/2, and then I used a logarithm property that allows me to move that exponent to the front. Those have nothing to do with derivatives. So I didn't put the derivative symbol there until I was ready to take the derivative. So now we can clean this up. Our 2 would actually divide into that 12 6 times. So that could give us a 6x squared over 4x cubed plus 1. And again, because of this addition sign there, I cannot reduce my 4 and my 6 or my x's. Everything goes or nothing goes. So now let's work on example B. It says the cost to produce X number of items is produced by C of X equals 3,500 times the natural log of the square root of 2x cubed minus 950. We want to find and interpret the marginal cost at a production level of 100. So let's find the formula first. Some people try to plug in that 100 right off the bat, but remember, we have to know what it looks like before we actually plug in the 100. So the marginal cost function is the same as the first derivative, will just be interpreted slightly differently. And looks like we're going to be using the chain rule because we have a function within a function. So let's take the derivative of the outside piece. So that's 3,500 times the derivative of the natural log. So that would be 1 over the square root of 2x cubed minus 950 times the derivative of the inside function. And I would rewrite that inside function again with a 1/2 exponent. So we don't have to deal with that square root. We're going to have to do the chain rule a couple of times, because not only do we have the outside piece of that red function that I wrote, so that's going to be 1/2 times the inside function as itself. And then don't forget to subtract 1 from your exponent. That's using the power function. Now we have to multiply by the derivative of the inside, which is 6x squared. So you might want to pause the video and just take a look to see where all those pieces came from. And now let's clean it up a little bit. This first one is still 3,500. So notice here I just wrote the negative 1/2 as a square root down in the denominator. 1/2 means square root, negative exponent means reciprocal. I can reduce, the 2 goes into the 6 3 times. And also note, when you multiply a square root by itself, you just get the radicand, the part underneath. So we get 3,500 times 3x squared on the top, 2x cubed minus 950 on the bottom. That gives us 105,000, so 10,500 x squared over 2x cubed minus 950. And we could try to, simplify factors, see if anything reduces, but we're not really looking for the whole formula. They're actually asking us to find, and I'll do this in blue, the marginal cost at 100 items. So we can just plug in 100 now for all of our x's. So assuming I put all of that in my calculator correctly, we get approximately 52.524. And it doesn't say that the cost is in thousands of dollars or anything, so that would just be the marginal cost. So we can interpret this as, at a production level of 100, the 101st item would cost $52.52 to produce. All right, that's it for that one. Let me know if you have any questions. Bye.